High-energy particle collisions operate at an energy regime that temporarily mimics the exact conditions of the early universe. Capturing the remnants of these events require experimental apparatuses on a massive scale, like the detector volumes here at the Large Hadron Collider. The discovery of the Higgs boson in 2012 provided a mathematically direct mechanism, a portal, connecting the visible standard model to entirely hidden dark sectors. This connection is defined by the minimal Higgs portal, governed by a single coupling parameter, eta-s. Cosmological models require a large eta-s value, but direct LHC searches strictly limit invisible Higgs decays. Therefore, large eta-s values are completely ruled out by data. The minimal model is phenomenologically cornered. To resolve this mathematical dead end, physicists have to alter how the hidden sector is defined. To move beyond these limits, researchers use the nonlinear effective field theory, or HEFT, framework. This framework expands the standard Lagrangian. It separates the standard eta-s term from a new momentum-dependent derivative operator known as the eta-ks term. This specific parameter governs the kinetic portal coupling. If a hidden sector is strongly interacting, it will naturally generate these local momentum-dependent interactions below the symmetry breaking scale. The range of this effective theory is mathematically bound by a cutoff scale, denoted by lambda, typically set around 1 tera electron volt. Adding momentum dependence changes the search parameters. Instead of direct decays, we hunt for indirect anomalies. The baseline strategy for finding hidden sector particles relies on observing the prompt, invisible decay of a Higgs boson into two exotic scalars. Here is the decay width function for this kinematic regime. The total decay width relies directly on the sum of the standard eta-s coupling and the momentum-dependent eta-ks term. Because they can carry opposing signs, destructive interference causes the amplitude to drop to zero. The exotic particle becomes functionally invisible to standard LHC decay search algorithms. This chart plots the direct search constraints on the eta-ks parameter against the scalar mass, mapping high-luminosity LHC exclusion limits. At a mass of roughly 200 giga-electronvolts, the expected exclusion curve flattens. Direct search methods entirely lose their perturbative sensitivity. Because the kinetic portal mathematically defeats direct searches through destructive interference, detecting this hidden sector requires a complete pivot to off-shell kinematic anomalies. The alternative diagnostic method involves measuring radiative corrections to the Higgs boson's two-point function. This diagram illustrates how virtual exotic scalar loops physically modify the Higgs boson propagator. The derivative interactions we introduced earlier impart a specific HEFT operator structure onto this propagation. These new structures are parameterized by a specific coefficient known as a box-box. This coefficient mathematically defines measurable modifications to the physical Higgs fluctuations in the immediate vicinity of the vacuum. While ZZ production has non-decoupling Higgs contributions, the corrections generated by the virtual scalar loops are too minor to set competitive constraints on the model. To break the model's camouflage, we have to identify a specific physical process that is highly reactive to these exact electroweak loop corrections. 4-top quark production provides that prime target. The baseline production of these 4 massive quarks includes a defined tree-level electroweak contribution. This production process receives an unusually large 20% electroweak correction. That exact characteristic makes 4-top final states hypersensitive to any modifications in the Higgs propagator. This plots high-luminosity LHC constraints on the kinetic coupling parameter, based entirely on 4-top production. The flat constraint lines demonstrate reliable sensitivity regardless of scalar mass. This sets a tighter boundary than standard 125 GeV measurements, while the shaded bands map predictive scale uncertainties. Calculating these limits requires a specific mathematical trick, decoupling the Goldstone boson contributions by transitioning to the unitary gauge. This mathematical isolation allows physicists to interface the off-shell top-anti-top amplitudes directly with predictive Monte Carlo software. These computational efforts map directly back to the physical data gathered inside the accelerator tunnels. 4-top production serves as the definitive phenomenological probe. It successfully boxes in the effective field theory parameter space, exactly where direct decay searches fail. These particle-level interactions scale up to dictate the thermal history of the early universe. Cosmologists look for a strong first-order electroweak phase transition to explain baryogenesis. This requires a phase transition strength metric, denoted as psi p, greater than 1. The momentum dependence of the kinetic portal drastically modifies the thermal effective potential. It effectively changes the inertia of the thermal plasma. This chart maps phase transition strength, psi p, against kinetic coupling across scalar mass benchmarks. For lighter singlet masses, phase transition strength successfully increases alongside kinetic coupling. However, forcing psi p above 1 triggers massive invisible decay widths, instantly violating established LHC signal limits. The kinetic portal alters the math of the early universe, but it cannot trigger a valid first-order phase transition without breaking known collider physics. The kinetic portal addresses the severe tension between the thermal relic abundance of dark matter and the strict exclusion limits set by direct detection experiments. This chart isolates parameters satisfying observed relic abundance while evading direct detection. It reveals a critical survival zone, a narrow parameter band at roughly 55 giga-electron-volts with negative kinetic coupling. Here, the kinetic portal perfectly reproduces dark matter relic abundance while remaining completely hidden. The physical footprint of this specific dark matter model is tiny. It leaves a highly specific cross-section deviation of approximately 5%. Detecting a deviation that small exceeds current capabilities. It requires the precision measurements of future lepton colliders, such as the proposed FCCEE, combined with finalized high-luminosity upgrades at the LHC. The minimal Higgs portal model may be cornered by the data, but by applying momentum-dependent effective field theories, the math proves that vast hidden dark sectors can still exist in plain sight. We just have to use off-shell kinematics to find them.
Scientists are racing to unlock technologies. Breakthroughs in AI are reshaping our future. The future is arriving faster than expected.